Hi guys, in this video I'll be going over some of the functionality and design of our team's FRC robot. As you can see in the frame, we're a human feeder station stacker, and we could also manipulate totes externally, although we probably aren't going to do that. That's one function of these external fingers. As you can see, we're pretty tall. We're pretty much right at the height limit. We're about 77 3/4 inch height. We're actually a little bit too wide. We actually have to take off one of these wheels to get in transport configuration, but that's not big of a deal. There's just the number 10 screw holding in, and we're within our other dimensions, so that's not an issue. As you can see, we're using a slightly odd drivetrain with 2 Omni wheels mounted in one axis on the back of the robot and 2 of them mounted in another axis on the front. Now this is a slight of an issue because when you try to move sideways, the only wheels to move sideways are these front ones, and obviously these back ones provide resistance, so it's going to have a tendency to want to go that way when you want to go that way. However, we were able to compensate with this with programming, and we actually have a sensor which gives us an off-robot orientation. We could always compensate for that as needed, so it's not really an issue, and I could demonstrate that a little bit later. Now what we ended up doing was making the robot wide enough so we could actually get a container in the robot lengthwise. We're a little bit bigger than containers, so we don't actually have to fight the margins. However, we can't pick up a container sideways, so if the handles are on the sides, it'll actually get stuck. We'd have to drop it, reorient the robot, and then try again. As you can see, the way we pick them up is we have these flappers which grab it just underneath the little lips on either side, and that's how we're actually able to pick up stacks. The way we unload and stack them is we have a base plate which is about 2.5 inches off the floor with this soft squishy roller, which is a little bit higher obviously to always make contact. And because the heights between the scoring platform and our platform are so similar, there's a very little risk in actually ever toppling the stack when we try to score it. Going around it, the way we're actually lifting them is we have elevator with linear guides in all 4 corners. As you can see, there's rollers on all 4 sides of the square tubing, supported on the front and the back, going through chain all the way around in a square. You can see down here, driven by worms. Now we have one of these assemblies on each side where we have a SEM with a worm and then a worm gear. I'm not sure, I think the ratio is about 16:1, which gives us a pretty good power ratio coming out of these SEMs. I think we only draw about 25 or 30 amps when we lift the full stack. As you can see, there's a SEM assembly on this side and a SEM assembly on the other side. Now it's extremely critical to send the same value to both these SEMs so they stay synchronized, because obviously it's very difficult to backdrive these worms. So if these SEMs receive different values and come out of sync, there's going to be a lot of torque on the shaft, which could be a major problem. And the only point of synchronization is the axle back here. The elevators are actually independently suspended on a chain. So sometimes it's a little bit tricky keeping this thing synchronized, but we took that into account with our chain tensioners. So what we have to do is loosen up these bolts, and this whole assembly can slide up and down on the chain. So if something ever does happen, or we have to set it up, it's pretty easy to actually get them back synchronized, so that's not that big of a deal. For our external fingers, we have a PG with an encoder on it, directly on the shaft, with a little coupler, and then we have a swinging arm. Looking at the 2 fingers, you can see that they're a little bit different. One guy has a piece of angle on it, the other guy does not. Now we're still playing with this and seeing what an ideal solution will be, but these things actually serve several functions. One of the functions is to actually stabilize a stack when we have a stack of 6, which you could see in another video. So when we have a stack of 6, the elevator goes up, these fingers swing out in front, and they actually stabilize the whole stack. It makes it a lot more stable. Another function they serve is to actually get the containers within the robot. Another function they serve is it allows us to manipulate totes externally to the robot. The whole reason one does have it and another one doesn't is when we pick up the containers. With this piece of angle on here, sometimes it gets caught on this ledge, so what we decided to do was get rid of this one. So when we want to write a can, all we got to do is get this finger in that hole, and then it's pretty easy to actually write them. The whole reason these things are in here is to fill the gap for the totes. So let me get these things out of here, and I can show you that real quick. So in this position is our external manipulation. This finger comes straight out, and this finger is at an angle. Give me a second. You can see when we're manipulating externally in order to lift it, we support both points over here, and this is obviously straight, so we get as much mounting as we can. And on this side, we can only support from the front. As you can see, there's a gap here, and that's why we had a piece of angle on this side as well. So this could be straight out, and there was no risk of toppling it. Right now, there's a slight risk of toppling if there's vibration, but we've already come up with a few solutions for that. We just haven't attached them on here. And since we're not manipulating totes externally, it's not really a concern for us right now. But if we decide to do quad partition, we may add that back on there. So that being that, as you can see down there, we just have the roller. We have a little chain guide going to a PG. Most of the motors we're using on here are just big sims and PGs, and that's pretty much it. These flappers are not actually actively driven. We're using magnets as a latch, and then we're using servos as actuators. So when we go all the way down, there's a bolt down there which sticks out through this hole and resets this, which attaches it and latches. Then when we want to actuate it, we actuate the servo, and this flips down. Check it demonstrate real quick. So when it goes down, it gets reset, and then we go up to any position, and then we can actuate it as need be. So that's how our elevator system works. And when we're doing a stack, the driver just has to press a single button, and it'll do a complete cycle. So right now it's up with the stack, you hit the button, it goes down, and it automatically does the whole cycle, making the driver's job much easier. And then here's the stabilization. So go down. And then in this position is where we go to stabilize it. Now one thing we do here is these fingers are actually not driven. They go to this position and then they become unpowered. Oop, forgot to turn the roller on. They're powered until you turn the roller on. So turning the roller on, now they become unpowered. So these are actively being forced inwards until you want to unload, and the second you start unloading, they become unpowered, and then they just get out of the way as the roller gets them out of the robot. And then when you reset, they become powered again and go into the position. We actually control these fingers in 3 different ways. One of them is an unpowered state, one of them is positional state, and the other one is a current state, where we put them, where we just apply a constant current, so regardless of what it's hitting, it's gonna stall the motors out at a given current instead of trying to go in a position where it can't go to, and then we have a potential actually blowing up these motors. We've run into a situation before where if you try to make the finger go all the way forward, but there's something stopping it, it can draw an excess of 20 or 30 amps. So we've smoked this motor, but it still works. So we have several different modes to actually drive these fingers depending on what it's trying to do. Obviously when we unload, we just unpower them and they get out of the way as we unload. That's pretty much our robot. It's really simple, not much to it. One other thing I forgot to mention is we have these additional centering fingers. So when we hit the button, they'll align the tote to be centered, and when it's centered, there's no issue when we try to pick them up. So that's kind of an excessive mechanism for that functionality. As you can see, there's 2 motors, again, couplers, and then 2 fingers coming out. So other than that, the robot is pretty simple, works amazingly well. So guess we'll see you at the competition. One other thing I forgot to mention, which we still may or may not use, is our vision system. We have a Windows tablet up here running LabVIEW with a PS3i camera. The reason we're using this camera is because it can actually go up to 188 hertz, which is much faster than either the RoboRio or the tablet can run it at. But the nice thing about that is the low latency. Even though the tablet or RoboRio can't process the information that fast, the last frame it grabs was much quicker than with a much slower camera. So there's multiple reasons we're using this. One of them is obvious, well, the biggest one is the frame rate, but the other one is you can find these things for less than $10, which is quite amazing when you think about what other solutions are out there. Again, a Windows tablet runs actually about, you can see the graph here, around 30 to 40 hertz. So a 30 FPS camera would work for this function unless they optimize the code. There's a couple different tweaks I could do. I've had it running it up to 80 hertz depending on how much vision processing I'm doing. And then the tablet will just send the coordinates over UDP to RoboRio. So the tablet has the camera, processes it, extracts XY coordinates of whatever I'm looking for, and then over Ethernet cable, which isn't plugged in right now, it sends the coordinates to the RoboRio, and then all the RoboRio has to do is move the robot according to those coordinates. So it's a very effective system, very lightweight, and much faster than just the RoboRio. In fact, I was trying with the RoboRio earlier, and the amount of vision I was trying to do was just way too much for it to handle, and the frame rate was just unmanageable. So with this solution, there's a lot of things we could do. We might use it during autonomous. We may not. We might use it for supporting teleop. But so far, I'm just playing with it. We're not really sure if or what we even want to use it for. But that's pretty much our robot. Other than that, not much to it. All right, see you at the competition.